before, so we'll see what happens. Well, when I got to graduate school, I'd never heard of ortho and parahydrogen. Well, they'd only been discovered a couple of years before, but when I got to graduate school, there was a great deal of discussion of them. And there was also a great deal of discussion of deuterium, which was discovered just barely before I got to graduate school. And every time you heard this discussed, the name you always heard was Farkas, Farkas, Farkas. And so when we were told that he was going to appear on the campus, everybody was very curious to see the Wunderkind. And he arrived. Now, of course, I don't know if this is, but we'll see what happens if I push the button. Yes, so now I want to go back. Yes. Yes, thank you. We need the light, and I'm going to have to close the door if you want.
Pull the one in the middle down. The one in the middle down. Yes.
That's fine. But we can put it back up. I tell you,
the one on the... I'll get it.
I want to turn them entirely out.
Oh, well, I'll get them all out there.
There. And then after the second slide, you can put them up a little. I only need...
Put them out too much.
Well, as I say, the name that you heard all the time was Farkas, and this would start from the catalytic point of view with the Farkas mechanism. That was originally for the high temperature ortho-parahydrogen interconversion, but it was immediately applied without change really to hydrogen deuterium. So then we waited with keen anticipation to see what the Wunderkind would look like. And there he is. In the dark suit. To the left, this was in April 1935, I believe.
Right.
And the chap at our left is Harold Geshunovitz, who became head of the World Shell Research Empire. And in fact, the Sunshine Pharaoh, who died unfortunately very young. Now, the person who took the picture is over at the extreme right, and that's Kyoshi Morikawa. And he had, I think, the first camera I ever saw that had a time delay on it that you could push and then run and get into the picture. I don't think I saw. And in those days, it was a matter of Japanese proper politeness that if you took a picture of anybody, you had to give him a copy of the picture. And Morikawa was always very proper about that, which is why I have this picture.
What is the location of the picture?
The picture is in the graduate school court at Princeton University, and that is Dean Andrew Fleming West in bronze, who made Woodrow Wilson President of the United States. Well,
Excuse me, who is behind me?
that's Sunshine Pharaoh, who died quite young. Well, no, as I say, just about the time I got to Princeton, deuterium was discovered, and it was immediately apparent to H.S. Taylor that, well, he'd already started some work with orthoparahydrogen. It was immediately apparent to Taylor that deuterium was going to be important, and so he set up a factory. Well, it's only 1 part in 5,000 in water, but if you find a friend who has an electrolytic cell that's been used to produce hydrogen for some years and start off with the contents of that which he kindly gives you, then you will find you've got 1 part in 1,000. And then you recycle and keep on electrolyzing, and eventually you get down to 99 plus deuterium oxide, and Professor Taylor got 100 cc's of it. Now, of course, all over the place people wanted a sample, and he set up a committee, of which he was the only member, who would decide who would would get and how much. Well, one of the hopeful, is that focus? I haven't got a focuser here. Or is it just my eye? It looks to me like it's not really focused. There, that's better, even with my eyes it's better. Thank you. One of the people who wanted some was Everett S. Wallace. He was a professor of organic chemistry, a quite well-known man in the area of molecular arrangements, and later one of the first Americans to work on steroids. And he wanted to run this particular reaction to
It's a little button.
he would start with this compound, which he could make optically active, and the vulgar display of fonts is just to emphasize that there are 4 different groups here. So it was been fully resolved. This would be converted to the bromide, to the Grignard reagent, and then this would be reacted with his 1 cc of heavy water. Now, of course, none of these steps would be thought to do anything to the optical center, so this resulting compound should be completely chiral, but would you be able to measure its optical activity or not? Well, now this involved then working with 1 cc of a volatile organic liquid, exclusion of oxygen, light water, and so on, and organic chemists didn't do those things then. So Professor Wallace came around and said, "You work with vacuum lines, maybe you could do this." So I agreed to do that. One summer I did it. The result was a bit disappointing in that the answers, the rotations you could see was very small, and it would be probably best taken as an upper limit, but still it was a definite result in its way. Now, Wallace probably had, I must say, as much influence on me as H.S. Taylor did. Both considerable, but Wallace in particular got me interested in stereochemistry, and that's an ailment from which I've never really recovered. Well, after this and my first independent work, I looked at the racemization of optically active secondary butyl alcohol and some catalysts. Wallace gave me the alcohol. And then I looked at the reaction with heavy sulfuric acid of that material, the alcohol, and also this optically active hydrocarbon, which has, you see, 4 different groups. And I would have liked then, I wanted to investigate the isotopic exchange and possible racemization of this compound. But that now tells me I have to go back historically to somewhat earlier work here. And so let us go to the paper of the 2 Farkases and Radil in 1934. As Dr. Farkas mentioned, he at this point had gone to England and very much impressed Radil. So they did the hydrogenation of ethylene on nickel wire, and they made 2. Farkas may say they made 27. I say at the moment they made 2 important discoveries. One was that ethylene inhibits the orthoparahydrogen conversion. Also, it would later be found to do the same thing with hydrogen deuterium exchange. The other thing was they found that in addition to hydrogenation, making ethane with some deuterium, that there was a formation of exchange olefin, exchange ethylene. Now, at the same time almost, the paper of Horiuchi and Polanyi is published. And in this case, this is the original article. We start off with what we might now call a di-sigma adsorbed ethane, a term they couldn't use. It reacts picking up a hydrogen atom going to a mono-adsorbed alkane. And then one more hydrogen, and we have the ethane, and now it's ready to restart the catalytic cycle. So, what then is the mechanism of the previous slide? Well, in fact, this is somewhat like what Professor Tomorrow was talking about. If we're going to start with ethylene and go to butyroethylene, I'm going to ignore the concerted reactions. I don't believe in them, really. And but there are two basic ones. There's an associative mechanism in which you first add deuterium, and then you take off a hydrogen, and now you have your result. Well, this just uses steps of the Horiyuchi-Polanyi mechanism I showed you on the last slide. But now, Farkas preferred this mechanism, where he took off the hydrogen first and then added it, getting to the same point. Well, how are you going to tell the difference between these two? Well, for a long time there was some debate on this, but I think it'd be fair to say that by and large, for most of the time, Farkas lost. People generally preferred the associative mechanism. But I was something of an exception because we were looking at some hydrogenations of things like hexene. And now, if you take the exchange on platinum, if you take the exchanged olefin and the alkane and look at their deuterium distributions in them, they don't correspond well. There was much less olefin in the much less deuterium in the olefin, and I thought very likely at least a certain amount went through this mechanism. Well, to continue the history, I showed you a picture of Kyoshi Morikawa, and he published 2 papers on the exchange of methane, ethane, and propane in that order. And the temperatures are those where you get about the same amount of conversion, so you can see that the methane is pretty refractory and propane is much more facile. These created quite a lot of excitement at that time. These, after all, were paraffins, which means they aren't supposed to be very reactive. Well, now, this is the proper physical chemist's approach. You start with methane, you advance to ethane, and maybe finally to something as complicated as propane. Now, how do you analyze this in those days? Well, they did actually both methods. They looked at the HD ratio and the deuterium that came out of the reaction, and they looked at the amount of deuterium that had gotten to the hydrocarbon. That, of course, is just an average. And you don't end up knowing whether you've got a lot of deuterium and a little bit of hydrocarbon, or a little bit of deuterium and a lot of hydrocarbon. And what those people badly needed was, of course, a mass spectrometer. Now, before I go to the next one, let me just say that there wasn't really terribly much more that I need to mention now, except one paper published in 1939. There was a second Faraday Society discussion that our hero here went to. That one was on hydrocarbons. And he gave a paper in which he surveyed the history of hydrogen and hydrocarbons. He made suggestions for future research. He made some mechanistic proposals. And he had very thoroughly gone through the hydrocarbon literature on hydrogenations, of which there was already quite a lot at that date. And he'd read the papers by Vavon and Burwell and Willstetter and Hugo, and so on. He not only read them, he'd digested them. And for somebody who starts off as a physical chemist, I was very much impressed with that. Well, now, having gotten access to a mass spectrometer, we thought we could start on this. So we now took the optically active 3-methylhexane, which we had to make, and deuterium, and we passed it over a nickel Kieselguhr catalyst. It was the same one Morikawa had used, as a matter of fact. I mean, not the same catalyst, but it's the same batch. And we used it somewhat over 100 degrees. And what we found was that, first of all, there was a deuterium isotope distribution of all species from D1 to per-deutero, D16. And we found that there was indeed racemization. The molecule is racemized, and the moles of exchange to moles of racemization is about 1.6. Well, now since there's some D1, D2, D3, it seemed likely that we could safely say that almost every time a tertiary hydrogen was exchanged, the molecule was racemized. And we got a few physical parameters on this, doing the proper thing. No, we also looked at heptane, and it was just like 3-methylhexane as far as its exchange pattern was concerned, so that a single branch in the hydrocarbon didn't interfere with whatever process was giving this. And then we tried this compound, and that immediately led to something quite important. The maximum deuterium introduction was 7. That is, you saw nothing 1, 2, 3, 4, 5, 6, 7, but no 8, 9, 10, 11, unlike the preceding case. So somehow a double branch, a gem dimethyl group, blocked whatever was propagating this exchange process, whereas a single branch didn't, and that was further, see both of those aspects here. You could get 7 atoms exchanged. There was a good big signal from 7 atoms, but nothing from 8. So that whatever the exchange process is, you can have, it seems to involve an alpha-beta process, okay, but it will not in any significant degree involve an alpha-gamma or indeed a alpha-delta or so on. And that, this turned out to be correct, and it was an important item in what happened. Well, no, we weren't the only person at this time, people at this time interested in that. One of the people was Turkovich. Now, he in this case, he was primarily interested in the Fischer-Tropsch reaction, and he ran the isotopic exchange on what was then the conventional Fischer-Tropsch catalyst under conventional Fischer-Tropsch conditions, the same conditions he'd used to study the reaction itself. Well, methane was very slow. Ethane and propane were faster, and this was very surprising at that point, I think, that over half of the product was per-deutero, and this also applied to butane. Well, now he was working under rather drastic conditions for iron, and his rate of hydrogenolysis was 1/6 that of exchange, but still, presumably, that didn't interfere with his result. Well, I don't think Turkovich thought this was very interesting, because he never continued on it. But another chap who also at the same time was working, he published his first paper in 1951, in which he looked at methane and deuterium on evaporated nickel film. And he went to a rather high temperature, 230, and he found two main products were monodeuterol and the tetradeuteromethane. Well, now Campbell apparently seemed to like this, because he never got over it. He's still stuck in it, and as I was. So there were 2 successes and 1 failure in this group. Well, now, a couple of years later, he published another paper in which he now looked at 4 more evaporated metal films, but with essentially the same result as before with respect to products. And now then, he published a paper with John Anderson, who I think was his first research student. And now they went to ethane on 14 different metals. You can make a student work harder than the professor can work. And he had 3 categories of things. Molybdenum, tantalum, and tungsten, they went a lot of 1 and decline in fraction of material. That is, a D1 there is a fraction of exchange, and D sub I is that fraction for 1, 2, 3, 4, 5, 6, 2 periods. Rhodium and palladium had low concentrations of single exchange, rising to a maximum at the 6, and platinum went down and then went up. Now I'm going to come to cyclopentane, which was one of the key molecules for this work. And just to say a few things, sorry, pushing the wrong button. to any buttons. If you, this actually should perhaps for the present purposes be 25 to 200. That was an old slide. And you've got some exchange species and HD, and as I've already said, you've got species that went all the way from 1 to 10 in this case. And d sub I, I've said that is a fraction. Now then, cyclopentane is roughly a planar molecule, not exactly, it's more or less shaped like an envelope that's slightly bent up, which rotates, so it's flat on the average. And it's then got two different sets of hydrogen atoms. Those above the plane, and which of course are always written with capital H's, and those below the plane, the molecule always writes in small h's. So we will, I've accepted the natural convention here. And now then, in 1954, Anderson and Campbell published this paper, which was quite important. They reduced cyclopentane and deuterium on palladium film, 25 degrees. Pressure is rather low, only 1 torr of cyclopentane, and they had a leak into a mass spectrometer. It's a batch, as all their work was a batch apparatus, which meant they tended to employ rather low temperatures, because you put a lot of evaporated film in, you put a little bit of this material, and then you can wait a long time so that you would work at relatively low temperatures. And the extraordinary thing they found was that there was very little 1 in D1, a maximum concentration at D5, then almost D6, and a rise to a large maximum at D10. You might notice that that maximum at D8, which they didn't comment on, but which turns out to be real and significant. Well, we were busy working too at this point, and now we were working in a flow apparatus, and we even worked for a while with a flow apparatus and evaporated metal films. And considering the kind of flows you need to accumulate enough material to get enough optically active 3-methylhexane so you can put it in the polarimeter tube and read it, it made the thing a little bit difficult. So, well, we tried now not only nickel kieselguhr, but evaporated film, reduced nickel oxide, and we tried again the optically active 3-methylhexane. S stands for septane, which is commonly called heptane. We looked at 2,3-dimethylbutane, and I'll come back to that at the very end of the talk. Now, all of the molecules up to here gave a lot of perdutero. Neopentane was very slow, and it gave almost only D1, which you might have guessed that would be the case from what I said about the 3,3-methylhexane. And the cyclo C5 and C6 gave maximum to perdutero and no breaks. Now, this completely deviated from what Campbell had found, but notice that we're working at 150 to 200. And Tuxworth and further work discovered that this is just a matter of temperature. Generally speaking, as you increase the temperature, you increase the amount of heavy exchange material. And at the start, we had no means of knowing what's the right, most interesting temperature to look at. It turned out to be the lower temperatures than the ones we started with, by and large. And when we looked at cyclopentane now, and the flow reactive, there was no break between D5 and D6 if you were above about 140 degrees, which was what we'd seen before. But when we went down to lower temperatures, then we got the same result that Campbell had. And palladium is sort of a nicer material to look at for cyclopentane because you get much more of the 6 to 10 deuterium atom species, and it's easier to interpret. Now, one thing that did come out of Tuxworth's work that was a little unusual, and which, as far as I know, nobody's ever commented on, or probably nobody ever read the paper. I think we did the first structure sensitivity work. we were just lucky to have up the hall Pierce Selwood, who was in essence measuring particle sizes of nickel magnetically. So we could get from him nickel catalysts which had large and medium and small particles. And here's what happens when we ran heptane and deuterium. Now, you see at the extreme right will be 16 deuterium atoms, that's a per deutero, and we got the percent of each exchange species. And you see there's quite a bit of difference, in particular in the amount of extensive multiple exchange. Okay, those ones which have very little extensive multiple exchange had small particles of nickel. The ones with the largest amount of multiple exchange up there were the ones that had the large particles of nickel. And so here was a case not in rate, structure sensitivity not great, but in selectivity. Now, we could do some worry about what this meant. And this comes from that paper of Tuxworth I just mentioned. We could say that it looks as if you first started off with the vapor, you would first have dissociative adsorption, and then there was some process in which this species inverted, going from one carbon to the other, necessarily introducing a deuterium. And now if this came off, it could be, you get a dideuero, this could be a repeat, you get a trideuero, and so on. Well, now, this was fine, this kind of process, but how did it go? Now, initially, because we had found that 3-methylhexane, optically active, and the exchange rate seemed to be nearly the same, we looked for an intermediate in this step, which would be optically inactive, or which necessarily would give racemization. But Campbell's result with cyclopentane, which I just showed, was likely to be related to the racemization getting from one side of the ring to the other side. Remember, we had a big maximum at 5, then very little, and then a maximum of 10. Those were probably related, so then we began to think that maybe this wasn't so. And now what Campbell was really saying was this. He gave you two options, a simple dissociative adsorption or reactive adsorption. First going here, then going to the diadsorbed species, either by reactive or by simple dissociative adsorption. And these are just steps from the Horiuchi-Polanyi mechanism, of course. Well, this reactive adsorption has recently been pushed by Frenet and Gove, for example, but Campbell never pushed it again after his earlier paper. And I think the total evidence for it is rather weak. But there's one feature of this diadsorbed intermediate. What is its stereochemistry? I can have the diadsorbed intermediate, the asterisk represents surface sites now, and I can have it either staggered or eclipsed. And in his earliest work, when he was in that cyclopentane paper, Campbell was assuming it could be either staggered or eclipsed. Both were possible. Now then, just one word about adsorption of 3-methylhexane. If I take optically active 3-methylhexane and I let either D or L, any optical activity, and it goes to this diadsorbed intermediate and then comes back, it will come back unracemized completely. If it goes in with an inversion of configuration, it comes back with inversion by microscopic reversibility. So the mere formation of this will not give you any racemization. Okay, now Campbell, in trying to get from one side of the cyclopentane ring to the other, I've proposed this. Let us suppose I have a monoadsorbed cyclopentane, and now I just go alternately around the ring from alpha monoadsorbed to the alpha beta diadsorbed and so on. I'll exchange all, in this case, I'll exchange all of the capital H's. That would give me D4, these up here are unexchanged, so it's got an asterisk D4H5. Now then, Campbell proposes that you go to this species, this alpha diadsorb species. Now you've got this, you've taken off one of the little H's. Now, two possibilities exist, 50%. One, I put a hydrogen on in the same way, other, I put it on the opposite way. So, if I put it on in the same way, I get a deuterium here now, but I'm back where I was, so if this desorbs, I got a large peak at D6. This one will come off at D10. Well, you saw the Campbell's results. There was hardly any deuterium D6 species, and so therefore this mechanism will not work with palladium. It might perhaps work with some other metals, but on palladium it doesn't make any significant contribution. Now, Shem did the following work. Let's first look at the bottom. He took bicycloheptane. Now, this has two ethylene bridges, and those bridges have hydrogens which are rigidly held in eclipse conformations. This molecule, let me just say also, this one, the next one is stagnant. This would be 2. Okay, you find that D1 and D2 are large, D3 is negligible. So you conclude that the diadsorb species is eclipsed, and staggered is high energy and doesn't contribute. If you try that now to cyclopentane, you get the right result. You get 5 hydrogen atoms exchanged, then trouble in getting beyond that. Cyclohexane. Well, to get cyclohexane so that these hydrogens are eclipsed, you have to, of course, go into a boat conformation. But you can go to a boat conformation. And then you'll get a break of 6, very little 7, now a lot of 12. Now, let's think about cyclooctane. That ring is a lot bigger and flexible. And in fact, you can easily enough get trans hydrogens eclipsed with cyclooctane, and what people calculate as one of the most common conformations of cyclooctane has a pair of trans hydrogens. Therefore, you're not restricted to one side of a ring on cyclooctane, and you expect to see a maximum, the main maximum, at how many hydrogens does cyclooctane have? 16, I guess, at D16. And in fact, there's no break between D8 and D9, and further, D6, 7, 8, 9, 10, that region is very tiny. It has an enormous amount of the product comes out in the perdutero. What about the cycloheptane? Well, here, if you make a model, you will find that with some effort and strain, you can eclipse a pair of trans hydrogens. It's a little tough. Result. Cycloheptane shows a small break between D7 and D8, but the values of D7 and D8 are way down here compared with D14. So then, that picture will explain all of that, but it also explains something that wasn't immediately obvious, the exchange pattern of methyl cyclopentane. Are you listening, Doctor?
I'm listening.
Good. There was a marked break between 4 and 5, between 8 and 9, and a large maximum at perdutero. Well, if you think about the material in the previous slide, you will think that, well, if there are these 4 hydrogens, little H's, but there's no way they can exchange with this methyl. See, that would take an alpha gamma, which seems to be forbidden. On the other hand, the big hydrogen, this was one, can readily exchange with the big hydrogens on the methyl. So then we would expect that if we adsorb initially into the H set, you'll only get 4 in a break. If you adsorb into the big H set, you'll get 8 in a And then if you turn over, get on the other side by some undisclosed mechanism, you'll get a big maximum. And so if I add up this and this, then I get what I have. And since then there have been a dozen, at least, maybe more, hydrocarbons which give patterns which you can explain perfectly well in this method. Well, now to skip ahead a few years, we're now in some work of Sraga in 1966, and he took this cis-dimethyl cyclopentane. Well, now we've got only 3 atoms in the little h set, and we've got all of the other 11 in the big H set, 5 here and 6 here. Now what do we find? Well, when we recover the cis, which is the heavy line, there's a distinct break between 3 and 4, a sharp break between 11 and 12, and then a great big maximum up here at the D14, the per deutero. Well, that is just like the methyl cyclopentane. However, this time we get heavy degree of isomerization of the cis to the trans. The trans is shown by the dashed line. So we start with pure cis, but we end up with the mixture. And the trans is excessively exchanged. That is, the per deutero is over half the material. So that these could be perfectly well separated and analyzed on a gas chromatograph. Only complication was that initially we thought we had 4 compounds there. The separation of this trans, which is separated on our gas chrome column from the a deutero material. Well, what this is our proposed, now at this point we finally proposed a mechanism for getting from one side of the ring to the other, and it's a very simple thing. Simply here is I'm sorry, too many buttons. Here is a diadsorbed species, shown just like a simple cyclopentane. Diadsorbed. It rolls over. Well, this could happen by desorption as an olefin, coming up and coming back down. But the activation energy isn't that large. It's still got some binding to the surface, and not really very much. And now, notice what happens. We've gone from one side of the ring to the other. Here, I was on the side, I've exchanged all the d atoms, you see, on the material on the bottom, lower side of the ring. Now I flipped it over. These hadn't been exchanged. Now I got the H's here, but I flipped this pair of H's from one set into the other set by this operation. And so if this exchanges, I can exchange these by the standard process. And now I got D8, and if it comes off, that's what I mean, I've got D8, but not D9 or 10. And this corresponds to what we did find. There is always a maximum at D8. And indeed, there was in Campbell's work too. Now, I think it's been, I hope it's been obvious that there is a lot of information content in these exchange studies. You make one run and you got a lot of information content. And in the work of Sraga did a number of palladium alumina catalysts, and when he compared the exchange results, it was clear that there were 5 non-correlated processes going on. And that there had to be 5 different sets of sites. That you needed 1 for D5, D10, D8, and 2 for D1 to D3, and 1 for D1 declining, D2 declining. You had to have that many. Now, this means that if one takes such a catalyst and uses it for hydrogenation of olefins, you've still got 5 different sites. You're just getting everything mixed up in one case. It's like running a reaction with a mixture of 5 different but similar homogeneous catalysts. And that's certainly the case in all studies with supported metal catalysts, although not everybody has been willing to admit this. Now, I should again mention that as soon as the pi complexes were discovered, some people like to write the diadsorbed species as a pi complex. But as you see, the structures of the two are going to, as far as the carbon structures of the two, hydrogen, are very similar in the two. It's always been my claim that you could not distinguish between the two by isotopic studies. But Rooney has never agreed with that. No, so what does this is where the history stops, and anything is more is too recent, except one little item I'll mention. And what can one say? Well, the basic theory explains so many things, there's likely to be something there that's right. But maybe it isn't all right. In fact, one of the problems which we noted back in 1956 was the methyl cyclopentane cyclohexane exchange ratio over nickel was 16. And why should a cyclopentane exchange so much faster than a cyclohexane? And just recently, Don Takahara has found on rhodium silica the cyclopentane-pentane ratio is 35. Again, if the initial adsorption is to form the monoadsorbed species, why should this be so much faster for cyclopentane-pentane? The ratios are much smaller on palladium and platinum, and I hadn't worried enough about them for some years till I got to this rhodium. So Campbell had recently worrying about the fact that some exchanges, I'm looking at the second line, had recently worried about some exchanges giving a lot of D2, and he thought maybe you were losing 2 hydrogen atoms in a concerted process. Now cyclopentane would be all set up for that, and pentane wouldn't. One might try to get something there. And finally, that I've already mentioned that tetramethyl ethane, if you want to, it's got a large maximum of D14. Now, if you want to get from one side of that molecule to the other, you have to go through that middle species. That's the only way you can go from one side to the other by that model. But there you're eclipsing both methyl groups. That's going to be fairly high energy, yet the molecule exchanges beautifully and gives a large maximum. It doesn't worry about this. Same thing is true in the ready exchange of cyclohexane to give large per deuterose. You have to go into the boat conformation, which is expensive too. So that my present guess is that I think that probably this mechanism has worked out, and I've not said anything about later contributions to it after I stopped, which were made by Go and Rooney and some other people. I think there's probably a fair bit of truth in it, but I'm not prepared to guarantee that it's exactly